This video is about solving systems of linear equations in several variables. So several mainly meaning 3 here, but let's get some notes down. I'm going to call this method double elimination. That's not really an official name for this, but we're going to do this just by hand for now. And the following steps will do it. So first, if needed, we're going to organize the original equations with like terms and equal signs all lined up vertically. So that's just kind of a helpful step to get us pointed in the right direction. Secondly, we're going to pick two pairs of equations and eliminate the same variable from each pair to create a set of two equations with the same two variables. Now, that's a lot of words. Okay, we'll see an example of how that comes to life here. That's second. Thirdly, we're going to solve the pair of equations from step 2 as a system. That's where we'll use elimination or substitution that we know. And then fourthly, we'll substitute the results from step 3 into the original equation to find the third variable. Now, we'll have a few different solution types possible in these systems. We might get one solution. Of course, it will be an ordered triple now with x, y, z instead of just the x, y, since we have now 3 variables potentially. We could get no solution, which would be evident in step 3. Or we could get infinitely many solutions, and note we'll express the solutions to a dependent system of this type in an ordered triple format, which is similar to what we did with the 2-variable system we've already done. Let's try an example where we want to solve the following system. The first equation reads x minus y plus 2z equals 2. The second equation reads 3x plus y plus 5z equals 8. The third equation reads 2x minus y minus 2z equals negative 7. All right away, we'll want to make sure that everything's lined up. And as you can tell, vertically speaking, it's already there. The x's are lined up vertically, the y's, the z's, and even the equal signs. We want all of that lined up. If it is, there's really no rearranging to do with this, which means we're going to use this original setup. But once you get it all set up as you'd like, with everything lined up vertically, we're going to label the 3 equations we have here as Roman numeral 1, 2, and 3. This is just a really helpful tip in staying organized, and you'll see exactly what I mean soon here, okay? So that's our original 3 equations. Our first step in our notes above said we need to pick 2 equations and eliminate the same variable from each pair. Now notice each equation has 3 variables, so we could really pick to eliminate x, y, or z from any 2 pairs. Now there's no wrong answer to what variable you want to eliminate first, but there sometimes is an easier answer. And if you look at the way these 3 original equations are set up, you might spot that the y variables are probably the closest to being eliminated. They already have some positive and negative mixtures, and they're all 1 coefficients, so they're just plus or minus 1s. That will help us in just expediting our first step. So if we want to pick y, which again we'll make that clear, but there's really no set variable you have to eliminate first. Just for convenience, if we pick y, then I'll pick equations 1 and 2, and we're going to use those to eliminate first because they're already set up to do so. Notice the y coefficients are already opposites in those, so we won't have much to do to eliminate those. If I just copy equations 1 and 2 down, that means I have x minus y plus 2z equals 2. That's equation 1. Equation 2 would be 3x plus y plus 5z equals 8. And they're already set up to eliminate, as we mentioned. If I just add down, then the x's combined, x plus 3x is 4x. The y's eliminate, that's the whole point. And then the z's combine as well to get plus 7z. And then on the other side of the equations, we have 2 plus 8 would be 10. Okay, we're going to call this new equation we got after eliminating the y's equation A, and I'm going to label it that way just to be helpful and clear with this first step. We're now only halfway through step 1 though. If you go above and read that first step. We've only done one pair of equations. Now that we picked y to eliminate, we're kind of committed to that. We're also now going to pick a second pair of equations and eliminate y from that as well. Well, if you go back and realize that you don't have to do much work if you pick equations 2 and 3 next. So we'll go ahead and just pick those equations, copy them down as originally given. So equation 2 was 3x plus y plus 5z equals 8. And then equation 3, and remember, there's no adjustment needed to these, which is why we picked to eliminate y, just for convenience. We would have here for equation 3, just copying it down, 2x minus y minus 2z equals -7. We'll go ahead and add to eliminate y's in this set as well. For x's, 3x plus 2x is 5x, the y's cancel, and then 5z minus 2z would be plus 3z, and that's all equal to, on the other side, 8 minus 7, which is 1. Okay, can you guess what we're going to call this new equation? You got it. That's equation B. Step 2 in our steps listed above, I will now do in a different color just to help us out here. This is the step where we want to now use elimination or substitution and solve the system given by equations A and B. So just take a quick look at them. They have coefficients for x and z. We need to eliminate either one of those variables. I just might pick to eliminate x's given those coefficients of 4 and 5. That's just a choice. There's really no wrong answer. You could pick to eliminate z's as well. If I picked to eliminate x's for equations A and B, then I would take equation A and multiply it by, let's say, -5. Okay, so if I do that for equation A, that will give me a -20x minus 35z equals -50. So we're going all the way across equation A, multiplying by -5 for that result. Now we're going to take equation B. Remember, I need to cancel I've just kind of committed here to x's, eliminating. So I would want to multiply equation B by a +4, because that would give me a 20x. There's the elimination that's going to happen. But then a plus 12z equals 4. Now we're ready to eliminate. As designed, these x terms will cancel right out. Moving across, we have -35z plus 12z. That would give us a -23z equals, and then -50 plus 4 would be -46. Okay, this is looking good so far. We want to solve for z here, and we can by dividing by -23. That would give us z equals 2. Okay, so just like that, we found z. Now, that's only 1/3 of our work, right, because we have to find x and y as well. But if we know z, we're halfway done with the step of solving this system of equations A and B. See, now if z is 2, I can grab, I'll just pick on equation B for a second. If I bring down the original equation B we had, but plug in z as 2, that means I'll have 5x plus 3 times 2, there goes the z getting plugged in, equals 1. Okay, this means 5x plus 6 equals 1, which means 5x equals -5, which means x equals -1. Okay, so now we have x as well. As seen in our notes above, the only thing left to do would be go back and find the only other missing variable. We found x, we found z, we need to find y, but the only equation that involves x, y, and z would be one of the originals. It does not matter which of the originals we pick. I'll just pick on the first one here just because it's first. I'm going to recopy equation Roman numeral 1 and plug in what we know. We found already that x is -1, so in place of that x value, I'll put -1, okay, minus y, we don't know y yet, but then plus 2z, but we found that z was 2, so I'll plug in 2 for z, and that's all equal to 2. Now we can solve for y. This just means -1 minus y plus 4 equals 2, which means -y plus 3 equals 2, which means y equals 1. So now we found x, we found y, we found z. We can put it all together in a nice ordered triple in order alphabetically. So -1 for x, 1 for y, and 2 for z. And that would be the single solution. So this was a case of a one solution system, and that would be it. Let's try a second example where we want to solve a system of three equations. This time the system reads, first equation is x minus 2y plus z equals 3. We'll call that Roman numeral 1 in the same kind of organizational scheme here. Our second equation is 2x minus 5y plus 6z equals 7. Call that Roman numeral 2. And our third equation is 2x minus 3y minus 2z equals 5. You guessed it, we'll call that Roman numeral 3. Now remember, we want to make sure all like terms are lined up vertically and all equal signs. That's already the case here. If it weren't, we would focus on fixing that first, which means here our next step is to pick on a variable to eliminate. Now again, there's really no wrong answer for this, but given what we see with all these coefficients, my choice probably would be the z's because of the fact that some of the coefficients are a multiple of the other, like 6 is a multiple of 2, or you could say 2 is a multiple of 1, and there already is a plus and minus going on. So it might save a step or two, but again, really you could pick any of the variables to eliminate first. I'll just say here, we're going to pick z's first. So this is like our step 1. We have to pick two pairs to eliminate z's. Well, why don't I start by picking equation 1 and 3. I'd have to multiply equation 1 by 2. Okay, if I do that, I would end up with 2x minus 4y plus 2z equals 6. My whole point is to eliminate the z's. If I look at equation 3, it's already set up to do that. So I'm just going to drag that equation in, which is 2x minus 3y minus 2z equals 5. But notice now if I add, these z's would eliminate, giving me 4x and then a minus 7y equals 11, and we'll call that equation A. Now if I picked to eliminate z's, I've already done one step of that, but I have to go and do another pair to eliminate z's as well. This time I think I'll pick equations 2 and 3, and I'll probably multiply the equation 3 by 3, which would allow those z coefficients to cancel. So let's keep equation 2 as is, which I'll copy down as 2x minus 5y plus 6z equals 7. But now I'm going to take equation 3 and we're going to multiply it by 3 because, as we'll see, that'll help eliminate some things. So that will turn this into a 6x minus 9y minus 6z equals 15, right? We're multiplying everything by 3 there. Now I'm ready to add and combine. The x's combine to give me an 8x. The y terms will give me a negative 14y. And of course the z's cancel. So all the way on the right side, when I add down, 7 plus 15 will give me 22. So here's equation B. We have 8x minus 14y equals 22. As you'll recall, the next step is to do a solving the system with equations A and B. And we could use elimination or substitution. It looks like things are pretty set up for elimination. Let's try equation A, but multiplying it by negative 2. Okay, that would result in a negative 8x plus 14y equals a negative 22. And then if I take equation B and just drag it down as is, that's really an 8x minus 14y, you can kind of see where this is going already, equals 22. All right, so if I add down vertically, everything's lined up, the x's drop out, but so do the y's, and so do the other numbers, which means we have a 0 equals 0 scenario. Now, do you remember what this means? It doesn't mean no solution. This is the case where there are infinitely many solutions, and we want to be able to represent their solutions as follows. Now, in the case of infinitely many solutions. As we saw with systems of two equations, we're going to do a very similar trick to represent all possible solutions, but now we have three equations. So it's not a whole lot different. We're going to start by focusing on equations A and B, and we're going to solve either one of them for one of its variables. It does not matter which, so let's just pick on, let's pick on solving equation A for x. So if I take equation A but solve it for x, that really means, let's see, 4x equals 11 plus 7y, if I just add the 7y to both sides, which means x equals 11 fourths plus 7 fourths y. Okay, so that's what x is going to represent. Now that we chose to solve equation A for x, okay, remember this is all, there's some variation in this. You could have chosen to solve it for y or picked a different equation. That can be frustrating to have so much freedom here, but let's follow this one through. We chose to solve equation A for x. Notice we have x now in terms of y because x is alone and the y is on the other side. Our next step is going to be to go back to, this time, one of our original equations. And if we've solved x for y, x in terms of y, our goal now would be to solve z in terms of y as well. And we can pick any of our original equations to do that. I'll pick on equation 1, just because it's equation 1. It looks simple. That equation is written as x minus 2y plus z equals 3. But remember, I've already solved for x. Now I want to try to solve for z. And we'll do it as follows. We'll just say z equals, if I bring everything else to the other side of the equation, I would have z equals 3, that was already over there, minus x plus 2y. That's just moving all the stuff over there. Now, I have z in terms of x and y, but notice I already know that x is written in terms of y in this previous step. So what we're going to do now is say that z is really 3 minus x, which is actually 11 fourths plus 7 fourths y. Okay, there's the x, and then plus 2y coming after that. So now we could say that z is really 3 minus 11 fourths minus 7 fourths y plus 2y. Okay, so it's kind of crazy to put all this together, but we now have x solved in terms of y. We have z, but let's clean this up a little bit more in terms of the arithmetic here. Let's just say z equals, now when you have 3 minus 11 fourths, okay, well 3, if you do a common denominator, would really be 12 fourths. So 12 fourths minus 11 fourths would be 1 fourth. And then if you have negative 7 fourths y plus 2y, again, if you put a common denominator of 4, that's really a negative 7 fourths y plus an 8 fourths y, which would mean a plus 1 fourth y. Okay, so now we have z in terms of y. We can put this all together by saying the x expression we got above, so 11 fourths plus 7 fourths y, that's what x represents. Y is going to represent itself. Notice it's what's showing up in both of these equations, so we just put a plain y. And then for z, we're going to put what we just found it to equal, which is 1 fourth plus 1 fourth y. And so this triple will represent all infinite solutions. Now again, some authors may get a little fancy and say, well, let's let y equal t, which represents any real number. And then they may say, okay, everywhere I see a y in this expression, I'm going to write t. Okay, fine. Same thing then. Really, it's just going to be 11 fourths plus 7 fourths t. That's the x value in our triple. The y value is just t. And the z value is 1 fourth plus 1 fourth y. Okay, so this could be an answer as well. It doesn't really matter. Furthermore, and this is often really frustrating with these, but if you go back and observe what we just did in this last step, we chose to solve for particular variables just by choice, right? We started here solving for x in terms of y, and then we just kind of carried that idea to solve for z in terms of y. But what if I had chosen back at this step to solve for y in terms of x instead of solving for x in terms of y, right? That was just kind of a choice I made. And actually, that's a valid option, and that's what's frustrating. If you went that route, your answer would actually look different, but it would be the same kind of answer. You'd have a bunch of variables in your ordered triple, but they would be different numbers depending on that route of solving. So when you're checking your answers, like in the back of a textbook or something, it can be frustrating if they pick a different variable to solve for than you did. But the main thing is to show your work and follow it through, and you should be able to find that this is the formula to represent any of the infinitely many solutions to a system like this.